Okay, so we're going to go ahead and start. Hello everyone and welcome. My name is Eric Glenn and I am the program manager for safety. We appreciate you all joining the webinar on use of disruptive technologies to support safety analysis and meet new federal requirements. You all have come into the meeting muted, and we would appreciate if you stayed muted until the Q&A session. If you have any questions during the webinar, please type them in the chat box and we will address them at the end. At this time, I'd like to introduce the presenters. Dr. Ioannis Sapakis, he also goes by Yanni. Dr. Yanni is an associate research scientist at Texas A&M Transportation Institute. He has more than 15 years of experience related to traffic volume prediction, data mining, applications of GIS in transportation engineering, and traffic safety. He has led several studies that dealt with AADT estimations and safety analysis using advanced data-driven methods. Next is Ali Kodidadi. Ali is currently pursuing a PhD degree in transportation engineering at the Zachary Department of Civil and Environmental Engineering at Texas A&M University. His main area of expertise is fundamental statistical analysis in traffic and road safety. Last is Dr. Subhashis Das. Dr. Das is currently working as an assistant research scientist at Texas A&M Transportation Institute. He has published more than 100 peer-reviewed research articles, book chapters, and research reports. He is an author of the book Artificial Intelligence and Highway Safety, which will be published in 2021. His area of expertise includes traffic operations and safety, advanced statistical modeling, and artificial intelligence. So without further ado, I'd like to pass the reins over to Yanni.
Thanks, Eric. So I have a few comments before we start. First of all, I was impressed that you got my three names correctly. Ioannis, Yanni, Tsapakis. Not many people do that. The other thing is that you can see maybe some boxes. So my apologies for the boxes, but I moved, over the weekend. And I have not been able to find a way to use a background image. So sorry for the unprofessional background here. So I'm going to start with talking about in general about the project. So in this project, we tried to do mainly two things. The first one was to determine the accuracy of annual average daily traffic estimates, AADT estimates, developed by a third-party vendor called StreetLight. StreetLight develops AADT estimates using a combination of traffic and non-traffic data, such as probe data. So we determined the accuracy of their estimates. And the second important component of the analysis was to determine the impact of AADT estimation errors on data-driven safety analysis that is recommended by the new HSIP guidelines, and they're also described in the highway safety manual. So my colleague Subhashis will join the presentation, and he's going to talk about the SPFs and the safety impact analysis that he did for Texas. And then Ali will talk about the analysis that he did using data from Virginia. So this is the entire project team. Subhashis was the co-PI. Dr. Lord from TAMU also participated in this study, and he's the supervisor of Ali. Eric from VTTI helped us to process, gather, and integrate data from Virginia. Ali, I already mentioned the work that he did. He was one of the main analysts in this project. Jessica also is an undergraduate student at UTSA, that's UT of San Antonio, and she helped to gather, process, and integrate data. I would like to thank the champions of this project for their help throughout the duration of the project, and many thanks our industrial partner StreetLight for providing us with thousands of AADT estimates for Texas and Virginia at no cost. Obviously, some of the objectives of this study could have not been addressed if StreetLight did not contribute to this project. So like any other presentation, I'm going to talk about why there was a need to do the study, the two objectives, how we prepared the data and the different types of data that we used. I'm going to briefly talk about the accuracy of AADT, and then I'm going to turn over to Subhasish and Ali and describe the SPFs that they developed for Texas and Virginia respectively, the safety impact analysis that they did, which was essentially a sensitivity analysis. And at the end of the presentation, we're going to draw the main conclusions. So somebody may ask, well, why did you guys do the study? I mean, what was the need for that? So back in 2016, there were new federal requirements for the Highway Safety Improvement Program. So these requirements essentially require states to have access to AADT, not necessarily submit them, but must have access for all public paved roads, including local roads. And by definition, local roads include the three lowest functional classes, that is rural minor collectors and both urban and rural local roads. So they must meet the requirements by 2026. And that was kind of a challenge for some DOTs because most of their budgets have been devoted to higher functional classes when we're talking about data collection and AADT estimation. So now the local roads is a new component that they have to deal with. The second component is, or the general expectation from the requirements is that they have to use the AADT in data-driven safety analysis by employing, if possible, advanced performance measures, such as the empirical base method. They have to develop safety performance functions and employ more advanced methods compared to, let's say, 10 or 15 years ago. So with that said, there are two objectives that we try to address. The first one is to determine the accuracy of probe-based AADT estimates that I mentioned before that were given to us by StreetLight. And the second one is to determine how, what will happen to the results of safety analysis if someone overestimates or underestimates the AADT using these alternative data sources. So I'm going to start with the first one. I'm not going to spend too much time here. So briefly, we gathered, processed, and integrated 4 types of data: roadway data separately for Texas and Virginia, crash data for a number of years, traffic count data that were provided to us by the 2 DOTs and include both permanent sites, but mainly short-term counts. Keep in mind that there is not that many permanent sites on the 3 lowest functional classes. And the 4th data set was 2017 AADT estimates that StreetLight developed using a combination of traffic data and other probe data from smartphones, GPS devices, and so on and so forth. So the analysis focused, as I mentioned before, on the 3 lower functional classes that you can see at the bottom of the slide for the 2 states, which you can see on the slide. We have maps of the 2 states. So I'm going to dive directly into the results. We had to compare AADT estimates from StreetLight versus AADT estimates from the 2 DOTs. And I'm saying compare because when you have 2 estimates, you cannot really validate. You can just simply compare 2 estimates. You don't know which of the 2 estimates is closer to the true AADT value. And the AADT estimates from the 2 DOTs have been derived for the most part from annualized short-term counts. So I'm not going to get into detail and explain each and every metric that we used. I'm just showing them here for completeness to show you that we considered many different measures. Maybe one of the most commonly used metrics that you might have seen is the MAPE or MAPE. It's the mean absolute percent error. And that's relatively simple to understand, and many people use it in the traffic monitoring world. So that's essentially the difference between the estimated AADT and the observed AADT divided by the observed AADT, and that the whole thing is expressed in a 100% scale. So this is a summary table that shows the main results disaggregated or aggregated by volume group. So you see 5 volume groups here, starting with 0 through 399, medium volume groups, and then the high volume groups. When I say high, it is high for the 3 lower functional classes that typically don't have extreme volumes. They don't have volumes that you would find, let's say, on interstates or freeways. You will notice here, not available. The reason for that was back in 2017, StreetLight did not produce AADT estimates for roads that appeared to have an AADT of 400 or less. So for that volume group, we were not able to do the comparison, but we were able to do it for all the other 4 groups. So in general, the 2 key findings is that the roads that have an AADT of 2,000 vehicles or more have a median absolute percent error of about 25%, and higher errors were observed for roads that have between 400 and 2,000 vehicles. I would like to note, though, that StreetLight has made significant improvements over time, and we've seen this kind of improvements in the accuracy of their estimates in many different projects, including an ongoing pooled fund study that is extremely exhaustive and comprehensive and does pretty much what we did, but for a number of states and for a number of benchmark sites. So just to put things in perspective, that 25% error that we calculated in this SAFE-B project, now based on preliminary results of the pooled fund study, that error has gone down to about 9 or 10%. So that shows that, and we've seen that also in previous projects, that StreetLight has improved in many different aspects their methods. Maybe they use more samples because the penetration rate of the smartphone devices continues to increase, or they might have made other types of improvements. So our guess or guesstimate is that the accuracy of these estimates, not only by StreetLight, but by other vendors, is expected to improve within the next 4 to 5 years, if not after that. And with that said, I'm not showing any of the other tables and scatter plots that we developed, because I would like this presentation to focus a little bit more on the safety analysis that we did. There are a few studies that deal with AADT accuracy, but there is not that many studies that have done the safety impact analysis that Subhasish and Ali did. So with that said, I'm going to turn over to Subhasish, who's going to talk about the SPFs that he developed for Texas. And then Ali is going to talk about the SPFs that he developed for Virginia. Note that Subhasish and Ali used different methods for the SPFs that they developed in the 2 states. So Subhasish?
Yes. Hey, this is Shubhashish. In next few slides, I will explain the safety performance function we developed for Texas. So here's the motivation of the safety analysis we conducted in this study. Yanni already explained the overall objectives and motivation for this project. So for the safety analysis, we find that in many low volume road or NFAS roadways, there are traffic volume data are not available. So that is one of the critical gap. And we also found that very few SPFs have been developed for low volume roadways or NFAS roadways. And another critical issue is the preciseness of the SPFs. And we also found that low precision accuracies in the available SPFs. So here's the overall contribution conducted for Texas data. We developed SPF for rural minor collector roadway for 2-lane roadways for 3 severity groups. We developed it for total crash or CAPCO crashes, KBC crashes, and KB crash. Those who are not familiar with the CAPCO scale, CAPCO is 5 different severity levels of injury: K for fatal, A for incapacitating injury, B for non-incapacitating injuries, C for minor injury, and O for property damage only or no injuries. So we developed model for 3 groups. CAPCO is total, and KBC, that is also known as fatal and injury crashes in high safety manual. And also we develop model for KAB crashes, that is fatal and serious injuries. And also one thing that is unique conducted in this particular study is that to improve the precision accuracies and to improve the precision accuracies, we applied decision rules to see the cluster effect in the data and to see that how the overall safety performance function will be improved by developing model based on the decision rule results. So what is SPF? I think those who are familiar with the high safety manual, they're familiar with safety performance function. So it is an equation in the following format that is shown from negative binomial model, and it predict mean crash frequency for a particular period of time for a temporal or for a temporal duration, and with a set of functions of with set of variables that we can be considered as a function of geometric and traffic characteristics. For example, this general model, it shows that the predicted crash is a function of traffic volume or AADT and segment length. So here is a image of rule-based model. How the decision rules are developed. So in the top panel, you'll see there is a box and it provided three measures, 1.28 and 11,000 and 100%. So 0.28 means that overall the KBC data, we see that there are mean KBC crashes on the segment is 0.28, and we found that there are 11,000 segments, and this represents the 100% of the data. So the decision rules goes like an if then statement. So think about here on the top, we are seeing that here the segment length is 1.2. If it is less than 1.2 and it is true, then we have to take a look at the left hand side of the decision tree. But if it is not true, that means the segment length is not less than 1.2, then the right panel. And then there are another clusters effect in the data. It shows that if it is less than 1.5, the average number of crashes or KBC crashes on that particular segment is 0.14, and we have 7,041 segments, and it represents nearly 63% of the data. And if not, then we are seeing that the number of average crashes is 0.54, and it represents 37% of the data. And then there are another clusters. So in total, we see that there are 4 different classes are produced from the KBC crashes, and we developed a model based on these 4 classes, as well as when we compared the complete data, and then we performed our evaluation to see that whether decision rule can improve the model accuracies. So here at the developed model, you see that there are 5 rows representing kind of 5 different classes of results. All means the whole data, but class 1, class 2, class 3, and class 4 represent the safety performance function developed for each of the classes. And also in each of the class, we see there are 2 rows. On the top row, we explained that it is the decision rule that is explained in the previous slide, and the bottom is the safety performance function for the particular model. And we also provided here over dispersion parameter and log likelihood for each of the models. This one represent the uniqueness of this study and the contribution of this study. So we plotted AADT versus predicted KVC crashes. So on the y-axis, we represent the predicted KVC crashes. On the other hand, in the x-axis, it is showing AADT measures. And there are 4 different predicted values or predictive values based on the SPF we developed for each of the classes, 4 classes, and the total data. And you see that even the SPFs are certain thresholds. Like for example, in the lower places, we see that class 2 in ash color, it shows that the AADT measure up to 300. And if you take a look in the previous slides, we'll show that how the clusters of AADT are used in determining those particular classes. So it definitely shows that by class-based analysis is little different from if we consider the whole data as a safety performance function. So we did also the validation. So here it is kind of a noisy graph, but I want to show it to show the overall contribution of this study. In the left-hand side, we see that there are 5 different cube plots that are developed based on segment length. On the right-hand side, we see that the cube plots are developed by each of the SPFs we developed in this model and by AADT. So cube plot shows the cumulative residuals. So here the result is in red line. So if the length is increasing in the, if you take a look in the left top panel for 6R KBC model, the red line indicates the SPF, how it is changing with the change of segment length. And there are 2 lines. It is called decision boundary and +2 standard deviation confidence interval. And if the cube plot resides within the 2 boundary, then we can tell that our model can take care of the variability of the data. That means segment length in this case, as well as AADT on the right hand side. And if you take a closer look, you'll see that in the 6R KBC model, there are slightly out of the boundary at the end of this cube plot when the segment length is over 20. But when we developed our safety performance function based on different classes, we particularly see that all of the decision trees are within the boundary. So it definitely validates our result that using decision tree helped improving the precision accuracy of the models. So that's all from the Texas-based analysis, but I'll come back again when we'll explain the safety impact analysis at the end of this presentation. So now Ali will explain the model he developed for Virginia.
Well, okay, for the Virginia data set, we tried to do a more detailed study and more in-depth investigation on safety evaluation and SPF development of non-federal aid system roadways. And we tried to come up with new models, or at least try to kind of improve the current models commonly used in the literature. And but what do we need to kind of try new models? Actually, negative binomial distribution is like the most commonly used distribution in crash frequency modeling. It's been used for decades thanks to its features like having variance mean ratio greater than 1 and accounting for natural dispersion in the crash data set. And they're actually really easy and simple to implement. We can get the expected values right after modeling the crashes. But when it comes to problematic data sets, such as data set containing a lot of zeros or highly skewed data set, and data set having a long, heavy tail, actually, the negative binomial distribution, the negative binomial family distribution cannot deal with it properly. They're not flexible enough. And we need to kind of try to remedy this issue, try to improve these distribution to kind of deal with this X0 problem, because X0 problem was our main issue in this project, since non-federal aid system roadways are typically characterized by different features such as lower speed limits, shorter segment length, and lower ADT values. All these features kind of contribute to fewer crashes on these roadways. And actually, this leads to X0 problem. So in the next slide, I'm gonna talk about the improvements we applied on the traditional negative binomial models. The first option is to change and modify the dispersion and variance structure. In the negative binomial distribution, the mean and the variance are actually connected through the dispersion parameter. This dispersion parameter could be could be formulated as a fixed value, as a constant value, or it could be defined as a functional on our data set and our explanatory variables. Like it could be a function of length, AADT, or whatever parameter we're going to include in the SPF models. By changing the dispersion parameter from fixed to varying dispersion parameter, we can increase the flexibility of our model and kind of make our model able to capture the structured variation and a structured dispersion in the data set. The other option is to change and modify the variance structure. We can change the exponent of the mean in the mean variance relationship and come up with different formulation of negative binomial distribution. We can come up with new variance structures like, the most famous models are negative binomial 1, negative binomial 2, and negative binomial p, which the digit refers to the exponent of the mean in the mean variance relationship. Each one of these distribution, each one of these variance structures can provide us with a certain level of flexibility, and we can find the variance structures and negative binomial structure that suits our data better. Next slide. The second option to improve the traditional negative binomial distributions is to use the mixture distribution instead of using the naive negative binomial distribution. For example, instead of having the shape parameter in the negative binomial distribution fixed, we can randomize it. We can put a distribution on it, assume a distribution for it, and treat it like a hierarchical model. In such mixture models, there are a lot of mixture models. There are a lot of hierarchical models introduced in the safety area, and they can be a proper proxy for naive negative binomial distribution. But actually, we chose negative binomial linear distribution, which showed better performance compared to its counterpart especially when it comes to crash data set containing a lot of zeros, suffering from the X0 problem. So that was our case. That was our exact case in this study. We were dealing with X0 problem. That's why we actually use negative binomial distribution as well in this study. I'm gonna just give you a short brief on our modeling protocols. In the first level, actually, we examined and tried two different distributions: naive negative binomial distribution and a mixture distribution, negative binomial linearly. And in the next level, we tried different variance structures. We tried three different variance structures, and then we applied 5 different dispersion structures in the last level. So in total, we developed 30 models in total and applied them on the Virginia data set. In the next slide, I'm gonna go over the results. Okay, as I mentioned, we developed and applied 30 models. Here's the best 6 of them. As you can see, almost all the performance measures like widely applicable information criteria, leave and out cross validation, MAD, MASE, and likelihood favored the negative binomial linearly models over the traditional negative binomial models. For example, if you take a look at WAIC, I can see the values are significantly lower for the negative binomial linearly models. And also results show that even within each family, the dispersion choice, the dispersion structure choice, and the various structures choice can considerably affect the performance measures. For example, negative binomial linearly models showed that they favored less flexible various structures. However, traditional negative binomial models showed they favored more flexible various structures. These results all indicates that to get more accurate and more reliable estimates, we need to kind of switch from the traditional models used in the literature to the new advanced models like negative binomial linearly with a reasonable choice of dispersion and variance structures. Next slide. We also observe the cure plots as well. Here's a cure plot for rural minor collector, one of the classifications of the non-federal aid system roadways. These plots are actually for the 6 model I presented in the previous slide. As you can see, the negative binomial linearly plots, for example, the red one and the yellow one, there's less falls and rises in these plots, and they seem to be more contained within the confidence interval. So based on the explanation that Sebastian provided you with for the cure plots, these results all indicates that the negative binomial linearly models perform better, and at least in the case of safety development for data set with a lot of zeros, or safety development for non-federal aid system roadways, it's better to switch from traditional models to the new advanced models.
All right, so I'm gonna briefly explain what we did for the safety impact analysis. So I thought that maybe the easiest way for you to understand the various steps that we followed was to give you an example. So let's assume for a minute that this is our sample network. The first thing that we did was to apply the empirical Bayes method. For those who are not familiar with the EB method, that method allows you to account for both the observed number of crashes as well as roadway and traffic volume characteristics. And based on all these factors, calculate the expected number of crashes at each site. So after we did that, we calculated an expected number of crashes for every single segment. And based on that, we ranked the sites. And after ranking the sites, we calculated the percentile rank of each site. And that's when the sensitivity analysis started. So we focused at each link separately. So let's assume the red link that is shown right there. For that link, we increased its AADT by X%, starting with 10%. After we increased that, we repeated steps 1, 2, and 3 for that site. Then we moved on to the next link. We increased its AADT by 10%. We repeated steps 1 through 3 until the entire network was scanned. After that, we repeated the entire process by increasing the AADT of each segment by 50%. And you can see the various percent increases down here. And then we repeated the entire process by increasing all the AADTs by 100% to 50, all the way up to 500%. So in that way, we were able to see how the rank of each segment changed when its AADT was increased by one of these percentages that you see down there. So that's essentially a sensitivity analysis, and we're gonna dive straight into the results. For Texas, Subhasish is gonna explain this chart, and Ali is gonna explain the corresponding results that he produced for Virginia. Subhasish?
Hey. Hello, yeah, here I am again. So this particular plot shows the safety impact analysis for Texas, kind of a little bit of too much information in the same plot. Here the blue indicates all data, and different other colors indicate class 1, 2, 3, 4 that we developed by using decision tree. But if you focus on one particular column, for example, this left one, we see that there are box and violin plot, and the violin plot indicates kind of a density plot, and it is kind of vertical density plot, and then it is repeated into both sides. And the width of the violin that indicates that the higher density for a particular Y value. For example, here in the blue violin plots, we see for 10% increase, it is almost the rank percentile. It's kind of 0 to kind of one, I think 0.5 or something like that. But when we increase the percentile by 100%, that we see that there are impact, and then the percentile rank changes. The peak will be around 1.8%, and then when you increase the ADT again for 200%, we see that the peak is also changing here, and similarly 250% and 500%. In the 500%, we definitely see that there are two peaks basically. One is on around 3, another is 4.2 or something like that. So it definitely indicate that the change of ADT that impact the safety analysis, and these plots gave a kind of visual representation of that impact analysis. So in the next slide, Ali can explain the safety impact analysis he did for.
I would like to make just one comment here, is that in general, the impact that you observed in Texas was not as significant as Ali will explain in the case of Virginia. So for example, by increasing the ADT from 10 all the way up to 500%, the rank of each segment changed, essentially the segments were ranked higher from a little bit above 0 all the way up to 4%. So that's not a significant impact, but the picture is entirely different in the case of Virginia. So Ali, would you mind describing the results?
Yeah, for sure. We did the safety impact analysis for the Virginia as well, and we did it in the exact same way Subhasish mentioned before. And actually, we observed the same pattern, not in the exact same extent, but we observed the same pattern as the AADT. As we changed the AADT in higher degrees, in higher extents, actually, the rank percentile for the expected crash values changed more rigorously. But the extent of the change in rank percentile for the Virginia data set was significantly higher than for Texas data set, and probably due to two reasons. First of all, we use negative binomial Linley in this data set for the Virginia data set, and negative binomial Linley models tend to be more flexible and more complex because they have more degrees of freedom, and more degrees of freedom means that they're more variance. So there's a trade-off between the bias and variance. We're going to get more accurate results. We're going to get less bias. So the variance automatically would go up, and that's one of the reasons that we observed more variance and more change in rank percentile when we change AADT values. The other possible reason for these results could be the fact that actually in the Virginia data set, we were dealing with around 3,000 roadway crashes, 3,000 roadways. But in Texas data set, we're dealing with around 400,000 crashes for all the low variance classifications. And that could be another reason that as the total number of the roadways is lower, so the relative rank percentile change is going to be higher compared to that of Texas data set.
So we reached our conclusion. So with regards to AADT, as you saw in the previous slides, the AADT accuracy improves as we transition from low volume roads to high volume roads. The median absolute percent error for roads with AADT greater than 2,000 vehicles per day is about 25%. But as I explained before, we used 2017 AADT estimates. Since then, StreetLight has made a lot of improvements, and we've seen significantly lower errors from ongoing projects that have similar objectives. And one more takeaway is that StreetLight now is able to develop AADT estimates for low volume roads that appear to have an AADT between 0 to 400. When we started this project, that was not an option back then.
And in regards to SPFs, we observed that rule-based SPFs perform better than the traditional SPFs. Also, the negative binomial Linley models outperform the traditional negative binomial models. In other words, these results are saying that we need to switch from traditional models and kind of try new advanced models developed lately that are developed specifically for a particular situation. For example, a dedicated SPFs for non-federal aid system roadways. Also, we concluded that the choice of the dispersion and variance structures matters both in negative binomial and negative binomial Linley distribution. Also, in regards to safety impact analysis, we concluded that negative binomial Linley models tend to be more sensitive to AADT accuracy due to that trade-off between the mean variance I mentioned. Also, impact of the AADT errors, AADT inaccuracies on network screening results depends on the AADT coefficient of the SPF, the overdispersion parameter, and actually the sample size of the network. So I think this concludes our presentation.
So we list here for those who would be interested in learning more about this project or even downloading the data that we used for the two states or even the SPFs that we developed. You can find the links here. We've already published, or I think it's in press, it's in the publication process, Ali, right? A journal article at the Accident and Health and Prevention Journal, and we're working on at least one or two more journal articles, and Dominic updated courses based on the results of the study. And he also included some information in one of his chapters in a book that he just published. And I think pretty much that's it. Please let us know if you have any questions, comments.
Yep. I do believe Mohammed Areza had a question. I think that I'll read it out loud. The effect of AADT accuracy was studied for segments relative to each other. What about the effect on the absolute predictive values?
So I'm not sure that I fully understand that. Are you referring to the predicted values from the SPFs? And feel free to unmute yourself if it makes it easier for you to explain.
Yeah. At this time, go ahead and anybody unmute.
Sure.
If you want to raise your hand, and then we can answer questions.
Yeah, thank you very much. Yeah, the ranking, the effect on ranking was showing basically, if say ADT is, the accuracy is within say 10%, how much that would affect the ranking, but not necessarily the actual prediction of the crashes for on each segment. The question is, for example, if the ADT is accuracy is within say 50%, how much the prediction of each segment would change. And that's not just for one segment, for many segments, and then taking an average or mean or something standard deviation, studying of the differences between predicted values of the same segments compared to for the same segments.
So that's a question for you, Subhasish and Ali.
Yes, I can explain it. So the thing is that I think, Yanni, if you can go back to the safety impact analysis steps. So we take a look at the estimation of ADT increase for 10%, 50%, 100%, 250%, 550%, but the ranks are based on expected crashes. So predicted crash is in the formula, like you know that in the EB method, expected crash is weighted factor into predicted value plus 1 minus weighted factor into the observed crashes. So we take a look at the expected crash and then re-ranking them, but not predicted crash. So that part also we can do, but we focus more on expected crash because that's what engineers use to get the expected number of crashes for safety performance analysis. Mohammed, did I answer it correctly, or
when you do this comparison for several sites in a network, this type of analysis is more useful for say for screening step of the analysis, network analysis. But when you want to, for example, do a safety analysis on a specific project or a specific segment, then this analysis is not useful there. To see, for example, how much the prediction on the same site would change if your ADT accuracy is, say, within 20%, 30%. That's for the same exact site. It doesn't need to be compared to the other sites in the network. So there are two different levels here. One is network level analysis, and one is project or segment level analysis.
I think you're absolutely correct. And I think the short answer is that we did not look at the difference between the predicted AADT value of each segment versus, its AADT value. We did it at the network level to quantify the effects system-wide as opposed to individual projects. But that's a good idea. I mean, that's a great idea to compare, the performance essentially of the SPFs by comparing the true AADT, or I'm not sure that they're true AADT, but it's essentially the AADT that we get from the DOTs versus those predicted by the SPF. Any other comments, questions?
This is in Lim. I have a question. Thanks for your great presentation. Can you hear me?
Yes.
Okay. Thanks for your great presentation. And then I was very happy to read all the papers and then put my comment on this. And actually, one of my questions was actually since we are focusing on the low facility types, means the very low volume or the widespread area in rural area. That means
Dr. Lim, I'm sorry I'm interrupting you. I can barely hear you. I hear a lot of background noise. I cannot really understand what you're saying. There's some little bit of echo.
There's echo here?
A little bit. I mean, there's some background noise that.
How about now? Okay. Better?
I think now it's a little bit better, I think. Yes.
Okay. Actually, one of my questions is, since we are focusing on low facility type, it means county roads has low AADT, but widespread area in rural area. That means when we develop the safety performance function, there's a lot of segments with zero crashes, means a lot of zero inflation. Do you have any issue from the too many zero crash segments from your data set?
Yes, I think Ali alluded to that. And Ali, would you mind answering the question?
Yeah.
About the excess zero problem issue that you described before?
So from previous research, some of the research recommend zero inflating, Poisson and negative binomial. So actually in Virginia case, I have been working for the Virginia, a lot of secondary roads in rural area have zero crashes for last 5 years or 10 years. So when we developed the traditional SPF, there was one of the concern and issue when we developed. So any thought from this?
Sorry, I barely understand the questions. Can you repeat it, Yanni?
So I think if I understood it correctly, when Dr. Lim developed SPFs for rural roads in Virginia, he had a challenge of dealing with a lot of zero crashes. A lot of crashes, essentially, a lot of segments did not have any crash. So the problem or the challenge is, how do you deal with these zero crashes in so many segments? So I'm going back to the slide where you briefly described how to deal with these excess zeros. So would you mind elaborating a little bit more on that?
Yeah, it's a very good question. Actually, it's all about the flexibility of our model, the ability of our model to capture the variation in the data set. So as I was saying, negative binomial cannot capture this high dispersion in the data set because the data set containing a lot of zeros tend to be highly skewed or tend to be having a long, heavy tail that traditional models cannot deal with. So I try to kind of empower the underlying negative binomial distribution, try to point those features that could be beneficial for making this distribution more flexible. For example, in the next slides, I was talking about the changing the dispersion and variance structures. We can kind of improve the model to deal with those excess zero by changing its variance and dispersion structure. Because I was saying before, it's all about the flexibility. It's all about the ability of the model to capture those variation. And also in the next slide, I proposed using mixture distribution instead of using negative binomial distribution. If you can tell me what kind of SPF model did you use for the Virginia data set, I can tell you why you had such problem with a lot of zeros in the data set. But in general, when we're dealing with data set with a lot of zeros, negative binomial linearly models have improved to perform significantly better than the naive negative binomial distribution that most of the people use in safety in SPF development for other classification, even not only non-federal aid system roadway classifications.
All right, thanks for your answer. Yeah, we applied the negative binomial, traditional negative binomial, when we developed the SPF, wasn't especially the SPF, safety performance function, but especially for the rural two-lane roadway, including a lot of secondary roads that consisted with the low AADT. So we had some challenges when we developed the SPF at the time. Yeah. Thanks for your answer. And then,
of course, no problem. Yeah, actually, collecting information is a challenge, is a big challenge. We actually faced with this challenge as well in these projects. We had to kind of deal with unavailable traffic information in couple of like so many roadways. We needed to collect them from different sources, combine different sources together to kind of make a complete data set that we can develop SPFs based on that. So yeah, I totally understand your concerns, and yeah, that's actually one of the problems that we face in this project as well.
thank you.
You're welcome.
Any other questions?
I think Mohammad Razat raised hand. Yeah, you can go ahead.
Yes, thank you. Very interesting research. Thank you for your presentation. If there were any opportunity to continue and using this data further, I would suggest that you also apply, I've seen maybe more than 95% of records and segments have ADT less than 2000. So relatively low ADT highways you're focusing on. If you apply the highway safety manual models to the same data and compare the results with your results, that would give an idea of how valid these highway safety manual models for these low ADT highways. And that would help other states to really know what they do. Currently, I believe whoever gets highway safety manual, they would apply it to all of their highways regardless of ADT. But knowing that with lower ADT, the results could be very different, that would be very useful. Thank you.
Yeah, that's a perfect idea actually, but couple of studies, not exactly in the scope of the non-federal aid system roadways, but in the scope of like low volume intersections and something like that. Last studies try to compare the HSM safety performance functions with the safety performance functions that they developed. They compared those, and as the SPF in the HSM are more for high volume and high volume roadways with crash frequency higher than a certain threshold. Those SPFs are kind of have been developed for roadways with high volume and high crash frequencies. So they're not exactly comparable with these roadways, but yeah, they use the same logic, but it's not like that the SPF in the HSM is gonna perform better than the one that are specifically developed for these classifications, because the assumption before those SPFs are different. HSM tend to lean more toward the high volume roadways, but we're dealing with low volume roadways. So basically, there are fundamental differences in here.
No, I understand that.
Yeah.
I don't expect that the HSM models perform better than these.
Okay.
Otherwise, I expect that these models would perform better because you're focusing on this basically level of ADT. The comparison would help other states to make sure when they do analysis on low volume highways, what they need to do, maybe an adjustment or something.
I agree. Essentially, that would give maybe a data point to them more evidence to either develop new SPFs specifically for low volume roads and not use those SPFs, more generic SPFs that are provided in the HSM. I think that's a great idea. Any other questions, comments? If not, the stage is yours, Eric.
So again, I'd like to thank everyone again for joining the webinar. I also like to thank the presenters for taking the time to present this webinar. I think it was very fruitful. There's a lot of great questions asked and answered. The webinar will be uploaded to YouTube, and I will notify everyone via email when it is complete. Our next webinar will be on examining senior drivers' adaptation to mixed level automated vehicles, which has a tentative date for May, and I will notify everyone who agreed to be on the mailing list the exact date and time. So again, thank you all, and look forward to seeing you on our next webinar. Have a good day.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, everybody.